Okay. Mm, I can. Okay. Hello, everyone. Still everything okay? Yes. Still okay. Thanks. Okay. Okay. In this session, we are going to exploit all the materials we've learned from information geometry to see its applications in different areas of machine learning as well as reinforcement learning. I start with a quick recap of what we've learned until here from the essentials of information geometry. Then I would go through the essentials of estimation and maximization algorithm. If you remember, we already discussed this algorithm in session 2, but here in a principled way, we would discuss exactly by the means of information geometry what does EM algorithm does. And then finally, we would go to the famous natural gradient, the tool that information geometry enables us to tackle a wide range of problems from optimization to reinforcement learning. Okay, quick recap. First, we defined a local metric of information metric, which is the Fisher information metric at each local point to be the Riemannian metric to make a Riemannian structure over the space of all probability distribution, which are parameterized by theta uh, within the second parameter, and we're talking about all the possible distribution over the random variable x. Then we discuss about the affine connection, the concept that enables us to talk about paths into a Riemannian metric. If you remember from the last two sessions, if I start from a point P and walk along a curve to get the point Q, or maybe it's better to say it in this way. If I start from a point P and given a vector field at point Px, if I walk through that x to get to the point P epsilon xp, very close to point x, the affine connection tells me what happens to other vectors. So y at point P plus epsilon x is y at point P plus epsilon, the affine connection of y with respect to x, which is if I go through the path x, how much the vector y changes. This is why we call it. So if we rearrange it, you can see why they call it a covariant derivative. So with affine connection, we can take derivative with respect to different vector fields. With the metric, we have a local inner product at each point. Then we discussed a wide range of alpha connections, which was given with this formula in order for us to give an affine connection, because it's a 3 new tensor. We need n to the power of 3 number of parameters to define alpha connection, which is defined as follows, for example, for the alpha connections. Then we went through 2 special cases of affine connections. One is for alpha equals 1, which we saw as the E connection or exponential connections. Why? Because if you put alpha here equals to 1, then all of this becomes 0. So walking through different vector fields is like walking through normal Euclidean space. It's flat. And we found the geodesics there, which is the exponential parameters, and they're simply lines. And also we found a dual connection, which made the space dually flat, which was the mixture geodesics. If we talk about the mixture of Gaussians, they are flat in the sense that if you take the alpha equals -1 connection between those set of those set of probability distributions, the geodesics would simply become lines. With this, we created a dually flat structure over the space of all probability distribution with the metric of information geometry. And we found 2 sets of natural coordinates and expectation coordinates. Last time we didn't have enough time to dive into the whole beauty of information geometry is because of the existence of this dually flat coordinate system. For example, if we, let me see if I put it here or not. Yes. For example, I can go ahead and calculate the essentials for this dually flat structure for a simple one-dimensional normal distribution. If we start with theta 1, I would use another parameter, C1 equals mu, and C2 equals sigma squared, to be given by x minus mu squared to sigma squared. This is the normal distribution. Then if we want to find the coordinates, the natural coordinates, we need to first find the function psi of theta. If you guys remember, we can show this same with minus x squared to sigma squared plus mu to sigma squared x and minus mu squared to sigma squared. And we take this to the exponent, which is 1/2 of 2 pi sigma squared. This is psi of theta. Now, we want to take the coordinate system for theta. We want to find thetas. So this is nothing but the exponent or the expectation coordinates. Here, eta 2, and this 1, 2 sigma squared would be eta 1. Theta 1, theta 2. And then we talked about the duality between the two flat coordinates. If we take gradient with respect to phi of theta, it would give us the dual coordinate system. So let me go ahead and write this. For example, here I would have, so if I take gradient with respect to the 2, theta vector of psi of theta, it would give me eta 1 and eta 2, which are nothing but the expected value of x and the expected value of x squared. So walking through this coordinates and lines would mean walking through the mixture model manifold of normal distributions, and walking through this would be an geodesic, an exponential geodesic would create us with the least distance with respect to the alpha equals 1 connection. And we saw earlier in the first 2 sessions that these two coordinates are dual in the sense that the psi and phi functions, when we write down the two probability distribution, these two would be a Legendre transform of each other. And also we defined divergence between the two with respect to these dual functions. Okay. Now, before going ahead and talk about the applications of information geometry, I wanted to introduce you to one of another very, very important concepts in differential geometry, which is exponential map and logarithmic map. Consider we are on a sphere. Let me talk about it in this sense. And we have the coordinates of 3 cities. New York City, we have Paris, and for example, Moscow. Sorry for the wrong geographical notation, but just 3 points, A, B, and C on the sphere. And C. What's the mean of these 3 points? If we consider these 3 points as Euclidean space, this would give us the geometry of a Euclidean space. But this is very obvious that the resulting point, the closest city on the sphere to all these 3 points, is not defined in this way because the resulting point would not be on the sphere. So we need to, and essentially what we do in Euclidean geometry is to take this vector to be the mean of these 3 cities. So In a way, we need to add and subtract points of a Riemannian geometry. That's where exponential math and logarithmic math enables us to do. For example, consider we want to define exponential math. Consider the point P on a Riemannian geometry and a vector V. Walk alongside the geodesics that results you with the point with the vector V. That's exactly exists one, and it's only one geodesic that starts at point P, and the curve's derivative at the first point is vector V. Walk through that for 1 unit of time. Essentially, it means that you have a curve. At time 0, it has point P. The derivative is V at time 0. And also, we have this extra condition that makes the gamma the geodesic. Then you parameterize this, and you have a geodesic. Okay. We call that point Q. In this way, we are able to, we'll see that we're able to add and subtract points. And now, we call the point Q the exponential map of point P with respect to vector V. And very same, we can define the logarithmic map to be given 2 points, P and Q. What is the autoparallel curve, which is a geodesic, that start at point P and end at point Q? Again, this is a set of ODE with an existing and only existing one curve that gives you this. Essentially, there exists one. It's not globally unique, but if the point P and Q are close enough, it's locally unique. It exists and locally unique. So we give a curve, gamma t, and then take a look at gamma 0. What's the derivative of gamma at the first point? And that is the logarithmic map. So here, if I write logarithmic QP, what is the vector V that if I take the exponential of the point P with respect to that vector, it gives me the point Q. It's like the inverse. But essentially, these two functions are all defined locally. For example, on a circle, if you consider the two poles, this set of ODEs do not have a global unique answer. So all these maps are defined locally. So we found the exponential and we found the logarithmic map. We have defined the connections. And now let's see in our example, what's the median point? What's the closest point to all of other 3 points? Again, when we talk about closeness in Riemannian geometry, we can go with 2 different notions, as we discussed earlier. One is the straight line, which is the geodesic, and it's related to autoparallel and connection. And one is the closest in the Riemannian metric sense of making a Riemannian geometry a metric space with respect to the G, which is the inner product or the Riemannian metric. Here, we mean the geodesic, which is the closest with respect to the straightest line. So we take the point A and we find the vector that gives us the point B. We show it with A through B. Then, if we calculate the exponential map of 1/2 of vector V A through B, starting from A, it would give us exactly the median of the two cities we had on the sphere. And then, essentially, if we do the same here, of course, with the, instead of 1/2 of the vector, if we go with 1/3, it would give us exactly the mean of the three. So on a non-Euclidean geometry, in order to take very simply the mean of 3 points, 3 vectors, you need to use the geometry. And by geometry, I mean the connection map. Now, in information geometry, you can consider the same question. Consider 3 different N1, N2, and N3 distribution, normal distribution. For simplicity, consider the variance to be 1. Then, what is the mean of these 3 distributions? We can come up with lots and lots of applications that has essentially this kind of question underlying. We have a belief system that the data we're observing is coming from either the first normal distribution or the second or the third. Essentially, all hypothesis testing is either the data coming from this or this or this. Okay? Now, we can change the connection metric, and we will change, I would show the mean of these 3 with respect to that to be the mean of the 3 mu1, mu2, and mu3 with respect to that connection. Again, if you change the connection, you're changing the concept of parallel. And with that, you are changing the concept of being the mean of 3 points. You are changing the geometry. So it's very funny. If you calculate this, if someone comes up with the following answer, that mu1 plus mu2 plus mu3 third and 1 is essentially the mean of all of this. It is the mean of all of this, but this is the exponential parameterization that gives you this mean. If you take the mixture model, for example, which when you are taking when you're taking a hypothesis testing, you're essentially talking about all these 3, the data A coming from normal distribution 1, the data B coming from the normal distribution 3. You're talking about the mixture model, not the exponential model. So in that case, it would change to some distribution which is not normal. So now we can ask the following question. You want the mean in what sense? Or when you're defining your optimization problem, you want the mean of these 3 distributions to preserve what? To be the KL divergence of the resulting mu hat to be this. The minimizer of this, or the minimizer of this. When you're taking the mean of three normal distributions to be this one, you're essentially taking an exponential mapping. So this is the solution to this. But when the question is the true data is coming from which model, you should calculate this. Why? Because you are now starting from a true distribution your data is coming from. And now you're saying, okay, out of all these different representations I used, one normal distribution 1, normal distribution 2, or normal distribution 3, which one should I choose? So you are doing exactly the opposite thing of taking the dual of the first connection, which is the mixture model connection. So after all these calculations, I will show 1 would be 1/3 of mu1 plus mu2 plus mu3. But if you take the -1 connection, first of all, it's not a normal distribution. Second of all, it would be the following thing. The first mu1, I can show it with mu2 dx, mu3 dx, alpha 1, alpha 2, alpha 3. And you're taking expected with respect to x, and you're taking to alpha i's. In what sense? When I say the minimum, or I should write it as the argmin, in the sense that the alpha I makes the KL divergence the least. So the resulting distribution is not a normal distribution. Okay, so I needed to talk about the exponential map as well, because you would encounter different kind of mean taking subtraction between points, which here is the normal distribution. Or you can come up with a lot of applications with this kind of understanding of distribution itself. For example, given the distribution I have, which is parametric, and given the distribution that the environment imposes with natural distribution, for example, the empirical distribution, I can find. So I start with a parametric model. For example, consider this as a normal distribution. This is what I have, and this is the empirical distribution. Okay. Now you can start from, this is the point mu hat, and this is the space, the manifold of all normal distribution, or this kind of parametric distribution. Now you can take a look at this curve. You can find the least distance between the two with different notions of the least, with different notions of connection, and then use that distribution. And you can start walking through this curve and find the optimization trajectory. Imagine not having access to these tools of information geometry. This would mean that you are just solving this analytically. You're not talking about the geometry of the distribution. You're not talking about the trajectory or anything. Okay, we'll see more about this in the empirical estimation maximization part, but I wanted to emphasize that the most applications we'll see or you can find online about information geometry exploits the tools we developed in the first 3 sessions with the 2 extra notions of exponential map and logarithmic map. Okay, we already talked about this. The whole bundle of information geometry boils down to Riemannian metric, which is differential geometry, the connection, the duality of connections, the duality of convex functions via Legendre transform, and the duality of divergences. And we saw earlier that all these concepts are very firmly connected to each other. That you start from a divergence, you would give the connection. You start with a connection, you will give divergence. You start with a convex function, you can talk about the divergence via this formula, and then you can create your geometry, and vice versa. You can start from anything in these 3 categories and build your geometry. So, and these geometry, we saw the equivalence between all of them. So this is a very strong tool we have that we can tackle different questions. Okay. Yes, of course, we already talked about the duality of geodesics and connections. And finally, we found this nice Pythagorean theorem in information geometry, which is, if you take a look, I think I have some, okay, not here. So if you parameterize your space with the eta, you see that the mixture model would create -1 geodesics, which are flat. And then if you parameterize it with natural parameters or exponential theta, we showed it. Then if you want to find the divergence between 2 distribution P and R, consider this as the whole theory of the relationship between connection, duality, divergence, and everything. If you want to calculate the divergence of these 2, you can start and walk through the M geodesic to get to the point Q. I can show it with another color, red. And then you can start and walk through the other geodesic, which is the exponential geodesic, E geodesic. And because we had this duality, we know that they are perpendicular to each other at point Q. The 2 E family and M family, because of the connection between inner product, which is induced by G, and the duality of connections. I won't write the whole thing. Because of this formula, we know that they are perpendicular to each other. It would give you 0 here. So you have this nice theorem of Pythagorean theorem, which enables us to calculate or walk through two different distribution with projections into E geodesics and then M geodesics. Yes. Also, I'm not sure if I discussed the sufficient statistics and information geometry, but essentially, as we saw last time, the eta coordinates or the mixture family coordinates, we can prove that for an exponential family, these expected value of x is sufficient statistics, which means they achieve the least variance. Why? Because it's like a very simple theorem. Because as we saw through the duality, let me see if I put it here. Yes. As we saw through the duality of theta and eta, we can start from parameterization theta. We calculate the etas. And then because of this theorem, we know that psi and phi are dual. So the inverse of the information of Fisher information matrix is nothing but the second or the Hessian of phi. So if we try to find the variance of this parameter eta, because of this theorem, it would essentially gives us the variance of inverse of Fisher information. And from the Cramer-Rao, we know that the variance of any unbiased estimator is lower bounded by the inverse of Fisher information. And we found the exact estimator to make this inequality exact. So we now know that the eta hat, which is if you take, for example, if you have n different observation, if you take simply the empirical mean and empirical variance, that would be a sufficient statistic. Okay. And also, because of the connection, I won't go through the proof of this. One can see that if you just have access to this sufficient statistics, that is enough to compare to the information loss between two distributions. It's the straightforward path of writing divergence between two different distributions, then h of x of these two would cancel out, and you would get this equality. So the whole information geometry, you can reduce the manifold. Instead of talking about x, you can start and talk about Sx, which is the sufficient statistics of x at each point. And by this, because the KL divergence of the two distribution remains the same after this map, so the whole geometry remains the same. No matter we start with what geometry in the first manifold, it would give you the same in the second manifold. So sufficient statistic is sufficient to talk about the geometry, which is obvious by the name, as the name suggests. Okay. Also, we talked about this. Yes. So we know that the E geodesic is simply a simple line in the natural parameter space, and mixture geodesic or M geodesic is linear with respect to taking the two distribution and talking about the convex combination of two distributions. And yes, consider this to be all around space, which is something called fiber. If we want to talk technically, but this whole two natural parameters would let you walk through the information geometry. And again, any Riemannian metric does not come with the dually flat. The whole idea here is that we introduced this information geometry manifold, and then we delved into this space, which is dually flat. We can come up with two coordinate systems that are parallel, perpendicular, and also flat. Yes. Foliation. Okay. Okay. Now I want to go ahead and talk about expectation maximization algorithm and its interpretation via information geometry. Any questions? Okay. Now I want to talk about estimation maximization problem, which we briefly discussed 2 sessions ago. This is the whole exploitation of the concept of dually flat structure on Riemannian geometry. Okay. Consider x to be a random vector with hidden part x. So we don't have the full information about the vector x. There is a hidden part h, and we are given the observable part y1 via yn. We want to find the best parameterization of the space x. So we want to find this theta over space of all distributions over x. That makes us very close to the true distribution, empirical distribution. So it's want to be as close as possible to but we don't have access to xi's. We have just partial observation. One way we saw it, if we observe the whole x, we can take maximum likelihood estimator and we're done. Here, someone might ask, why not to do the same here as well? So given any distribution, we go ahead and calculate this, the marginal distribution over y, which is done by taking integral with respect to all hidden hidden variables, and then estimate over this second manifold. But the problem may seem very simple when we talk about this manifold. For example, if you start with the Gaussian mixture model, as we'll see in what follows, this is very simple to write it down. But if you go ahead and But if you go ahead and calculate the marginal distributions, this would be intractable to calculate. So we have a parametric space. Consider this as the whole space of all distributions over X. This is all distributions parametrized, and this is the empirical distribution. Then we found via E projection, as we saw it, or the minimizing the KL divergence, what's the least information loss when you want to represent Q bar with a member of this manifold. This would result into MLE estimator. Of theta, of this Q bar, and this would be a E projection. But here, we don't have access to the whole empirical distribution. We have hidden variables. So, what's the solution? We start with writing down Q in this form. So we write Q as the distribution over Y, and then the conditional distribution of given Y of H. Given any distribution of Y and H, you can write it down as this. Then consider this as your data manifold. So the data could come from any distribution. This is 1 over n delta of y minus yi. You observe this, so this is a point. But this could change. Maybe the non-observed variables come from different distribution. You cannot assume they come from a single distribution. So you create this data manifold, which is essentially, this is some one point distribution. So this is essentially this space of all conditional distributions. And then by multiplying it by the marginal distribution we already have, we observed y's, you have the same distribution over X. Okay. This is your data manifold. And it's very easy to see that this is an M-flat submanifold of the space of all distributions over X. Why? If you take the logarithmic of this, log likelihood of this, it would Q bar Y, logarithm of this plus logarithm of QHY. And if you parameterize it because of this structure, it would give you an M-flat submanifold. So in a simple MLE problem, you had the model manifold, the all distributions, parameterized with theta. You wanted to find the best theta, which was maximum likelihood estimator from a single point. Now you have another manifold, which is the data manifold of QY of Y and QH given. So if you start from any point in the data manifold, then you can find the best. This is again a distribution. Yes, this is a single distribution of data. You consider your data comes from this distribution. Then you take the maximum likelihood estimator, which is the ES step, this gives you theta 1. Then this is again an M-flat manifold, as we saw. If you take the M step, don't forget, taking ES step is minimizing the KL divergence of the second distribution, and M step is nothing but taking minimization with respect to first distribution. You fix the second distribution. What is the first distribution that this distribution is the closest to? You get another belief that your data is coming from, I call it Q1. This is another thing, QYY, Q2HY. Then, given that, you take another ES step. It gives you a theta 2. Okay? In this way, you are not only taking optimization with respect to your parameter space, you're also taking optimization problem to your belief system of the data is coming from which point in this Riemannian manifold, of the data manifold. Okay. Maybe, yes, this is E geodesic. This is M geodesic. Of course, this is maximization. And this is estimation. Yes, ES step, sorry, the ES step and the M step are walking through M geodesic and E geodesic respectively. This is, yes, what I said was the correct way. So if this distance is minimized at each step, then with some regularity conditions, we can come up with a proof that the EM algorithm stops at the end. Yes, and we have that, that starting from any starting belief system in your data manifold, you would converge into a local minimum, because at each step you are minimizing. And because space is, we can consider this to be compact, we have, with some other regularity conditions, we have the convergence of the EM algorithm. Okay. If you haven't understood rigorously what happened, here we go with an example. Okay. Consider, as we talked earlier, a Gaussian mixture model with the same variance but different mean, and we're not sure what is the weight of different distributions. So we have two parameter spaces. If you fix W's, W0, I will show it with W0. This space is an E submanifold. And if you fix the mu's and you change the W's, this is an M submanifold. You're talking about all mixture models. Okay. You observe Y, but you don't observe W's. You don't observe which, so your data is of this form, X is of form Y, and its class. This is either 1, 2, or 3. So you're not observing the whole X, what normal distribution this X is coming from. So we create a data manifold, which is what? We create this manifold. This is our data manifold. So every distribution, the true distribution, would be ideally with some of this to be 1 for each data point and some of this to be 0 for each data point. By considering the space of all W's, possible Wj's, you are including those. Of course, you are including a lot of other data distributions as well. Okay. Now, at each step, if you remember, we need to start from an arbitrary belief distribution or prior distribution. So we need to specify Wj's just randomly, just they sum up to 1. Each data point is either coming from one of these distributions, but you start with random initialization. Then you calculate, so you fixed your distribution. You fix, now you optimize over the parameter space of mu's and w's. Then, based on that, you update your w's. So in the second step, you increase the probability of data I coming from normal distribution J, respectively. If the parameter gives it a higher probability, then you increase your belief over that specific normal distribution. And mathematically, in the first step, you are minimizing, you are fixing your parameters. So here is given Q that you optimize, you find the parametric P that best represents your belief right now. And then in the ES step, you're minimizing over all beliefs you could have over the parameter you got. And in this way, you're walking through different geodesics, and you are at each step minimizing the gap between the data distribution and the model distribution. So at the end, you will end up to a local mean. Okay. I think the EM algorithm is one of the most interesting parts of information geometry, because other than that, the other explanations of EM algorithm, of course, you can come up with a Bayesian maximum a posterior estimator of your parameter, and then you would come up with the EM algorithm. Or if you consider some heuristics, you can come up with the EM algorithm. But considering information geometry, you can come up with a very nice theoretical proof of what we are doing essentially at each point. Yes. Any questions for the second part of this session, which was the EM algorithm, E step, M step, E projection, M projection? Okay. When I was trying to find the most important applications of information geometry for anyone who's interested, I think the more explanatory way of considering information geometry, the way you understand information geometry is EM algorithm, but by far the most application everyone is doing with information geometry is through natural gradient descent. The idea is very straightforward. As we discussed in the motivation first session, we started with, is anyone talking? Okay, I don't think so. Okay. The most thing in different applications is natural gradient descent. The idea essentially is the same as Newton method. We are taking into account the geometry of optimization. So instead of optimizing simply like the space of parameter is Euclidean, we want to take advantage of the geometry we built on this space. Okay, this is a very nice explanation of why natural gradient descent works. Consider inputs x and targets y, like a regression or a classification. You can consider y to be 0, 1 classification task or a regression task. Then you assume that your data you observe is coming from a function x plus a noise. If you solve this via maximum likelihood estimator, you would see that you can solve this with the following, creating the following distribution. So you have defined this probability joint distribution. And then because you have access to y and x, but not f of x, you create a distribution or p in this. And then you go and find the best, this is the space of all distributions. Essentially, you can parameterize it by parameterizing the function theta. And then you go ahead and find the minimization, an E geodesic, or a minimization of KL divergence over this empirical distribution and this space of parametric distributions, or essentially taking the maximum likelihood estimator. As we saw, minimization of KL divergence is the same as that. Okay. But if you want to consider you have too many data, or you don't have access to the whole data, you don't have access to the whole distribution of X, you just have access to a limited number of observation and input points. So in this way, you need to minimize this loss, but you don't have access to your whole distribution of P, X, and Y. Or the X and Y takes a lot of memory, or you have other limitations. So what you do is to take an estimation of the gradient of your function. What's the estimation? You take the gradient of that observed points at each round, and then you simply take a step toward that gradient. What's the problem here? The intuition behind gradient descent is that you want to find the steepest direction and then walk through that. Yes. And then walk through that direction. But the step you want to take, if you don't take into account the geometric properties of your space, you may take different step sizes. For example, in one direction, if you go 1 meter, then of course it would be much more steep than going to another direction, but for 1 centimeter. But the whole idea is that the steepness in the second case is much more. So you need to take into account what step you are taking. And that is nothing but the curvature of your space. Okay. If you remember, in the Euclidean space, the distance is given by this Euclidean form. But the whole idea of information geometry is that the distance has already changed by considering this Riemannian geometry. So if you go into I and J, it would create a length here if Gij is not 0. Whereas in Euclidean, it would not matter if you take both your steps in I or both steps in J. Okay, so here we need to take into account this metric. Okay. Now, I say this. Okay. I want to take a unit step. By unit, I mean the norm is 1. Remember, the norm is different at each point, and the norm is different with respect to the inner product. So I want the step I take to have 1. When we consider this, we already are taking into account the geometry. And then we want this step I take to be maximized. Maximum of alpha, which direction? To be maximized, which is aligned. This is simply inner product in Euclidean term. So I just write it as alpha L. And then I want to, with respect to the fact that the norm of A is 1. If you write the Lagrangian of this problem, it would be this. And then if you take gradient with respect to A here, you would get that A is given by the inverse of Fisher information matrix times the gradient. I can go ahead and write it. So this is dot A minus gamma A G A. And then if you take gradient with respect to alpha, A G A would be this. And so A is nothing but this. So the steepest step is given by this formula. We just took into account the condition that the step we're going to take is unit, but it's unit in not Euclidean term. in the understanding of the geometry of the space itself. And then we get this second operator, which is the natural gradient operator, of not only taking the gradient, but using the inverse of Fisher information matrix. Okay. And now, of course, we don't have access to the whole space. We just estimate the inverse Fisher information. We do this with respect to the data we have. So we take, for example, the n samples we observe and calculate the log likelihood and the Fisher information, being simply the empirical mean of each point. And then taking this step. Okay. Why this method works? So again, this is natural gradient descent is of course a gradient descent, so it converges essentially, but the speed of convergence is much faster in this way because we're taking into account the curvature as well. So one thing to compare at is the following. The difference between Newton method and the natural gradient method. So I forgot to put it here. So here, when you take the Hessian of your loss function and then use that Hessian to inversely impact your step, which is again some notion of curvature. But if you were considering the information curvature, exactly this is not what you're looking for, then this is this expectation is with respect to the true distribution. At each step, you are considering the loss, the expected of loss with respect to the true distribution, although you started from some other distribution, some other parameter of the true parameter. Okay. But in the natural gradient descent, you are taking expectation with respect to the point you are at that point as well. So that's the only difference. And at the starting point, if you both consider the starting point of the algorithm, then the two Newton method and which is the Hessian, and the Fisher information method is the same. But when we have singularity with respect to Hessian, then of course the first method doesn't work. But it is the case for the natural gradient descent, which enables us to optimize a lot of things, like multi-layer perceptron, because we have this kind of singularities a lot in multi-layer perceptron that enables us to take natural gradient descent and still make sure that we have a fast convergence. Yes, this is... Yes. So again, this is a quick recap of Newton method, because we're just considering the Hessian of the matrix and then taking expected with respect to the initial distribution. This could be very unstable when the H is going to be close to zero. But the natural gradient descent is not only taking advantage of the true geometry, not a heuristic of the true geometry, but also robust. We are regarding those saddle points. And yes, this is also natural gradient descent. I don't think I have enough time to go over this, but I wanted to talk about reinforcement learning and natural gradient descent. Okay, this is just a very brief explanation of natural gradient in reinforcement learning. A lot of this specific part is just for those who are interested and are familiar with reinforcement learning. Consider you are in an MDP. You take action A at the state S, and that thing is parameterized. And of course, it is stochastic. Then you get a reward RT, and that reward is summed over time with a discount parameter gamma. Then the objective is to maximize the return. You want to find a policy, and the policy is nothing but given a state, and a parameter gives you a distribution over all possible actions. Okay? And then this is policy gradient in reinforcement learning. You start with a parameter, you take gradient of that, a policy gradient, and then you optimize that. Just this time, instead of descent, you are doing a gradient ascent because you want to maximize your reward. Okay. Here we can also take, instead of taking the expected of return and the gradient of your policy, we can take into account the geometry of your policy as well. And that is nothing but to take this. You are taking the Fisher information and you're using the inverse of that. This has a lot of applications in PPO, TRPO, and all these applications. You can, they use this G-matrix because they exploit the concept of the curvature of your space. And then you optimize over that parameter space. Yes, and also something very important, because the distance of the induced distance of metric is independent of parameterization. If you want to use a neural network for your policy, which is usually done with the deep Q networks and everything, you are using parameterization of your policy. You want to find a robust policy and the optimization path that if you change your policy, the path remains the same. That means that you want some policy, you want some gradient ascent algorithm, which is robust to change of parameterization. And because of considering the curvature, you can achieve this. And this is proven to be much faster than the usual vanilla gradient ascent. So also, yes, so the material we had for today was considering two main algorithm, estimation and maximization algorithm, and the another was the natural gradient. I was looking into different applications of information geometry in machine learning, but to be honest, the analysis it gives you is very general, of course, other than natural gradient ascent or descent, whether you're optimizing a maximization or a minimization problem, which is very practical. Other aspects of other applications of information geometry in machine learning is reduced to understanding different algorithm via the perspective of information geometry. For example, you are optimizing a neural network, then you take a look at your optimization path, and then you can visualize it via information geometry, and it gives you a better understanding. Or you can take a look at support vector machines, and then consider the kernel method there. And instead of just solving through kernel method, you can create the geometry out of your kernel methods, and then take a look at that algorithm via the perspective of information geometry. For me, the most interesting part of information geometry in the whole area of machine learning is the different understanding of the data distribution. So, for example, you start with a uniform distribution, which I show it via Q bar. Maybe it's good to write it down in a new. Yes. So consider this. Okay. This is very general. You start with Q bar. Then you can understand anything from understanding the geometry around Q bar. Let me explain. For example, if you want to optimize over your training data, but you have this problem that maybe the data is biased, maybe some of the data is outlier, then how can you theoretically formalize your problem? So you need to take a look at, instead of optimizing p theta and finding the best distribution, which is MLE, for example, in this case, if you consider KL divergence, then you want to optimize over the true distribution. So the true distribution Q is Q bar with every data point. Some of them are weighted 0, and some of them the weights increased, or an importance sampling procedure. Some of the samples are much more important to your optimization problem. Then you can visualize that as this and if you consider different omega i's, this is a simplex, which is, of course, a mixture model, your data distribution. And this is your model, data manifold and your model manifold. So you can understand the whole procedure of importance sampling, distributionally robust optimization. Or if you come and talk about the mixture of parametric spaces, you can talk about the boosting algorithm. So it gives you a perspective of all this from this view, okay? For example, one solution could be to simply, instead of going for this as your answer, to try to find the best curved prior distribution or prior Q bar, which is also close. This is a very intuitive way of talking about distributionally robust optimization. But we never studied distributionally robust optimization, but it seems very natural with the tools of information geometry to talk about that. So for me, the applications of information geometry in machine learning is more of an explanation or an interpretation of the algorithm in machine learning rather than building some new algorithms. If you understand the existing algorithm through the perspective of information geometry, it would give you this sense of creating new algorithms. And of course, the whole area of information geometry, the whole idea boils down to this two canonical divergence and the two flat structures we already found in the machine learning. Of course, theoretically, you can go for different alpha connections and exploit the dually flat space that kind of connection gives you. But for the sense of considering different machine learning algorithms, because if you're taking an estimation, you're walking through an e-geodesic, and if you're doing a maximization, you're essentially doing some m-geodesic paths. So the whole idea is to find the sufficient statistics, to find the eta coordinates, and then try to understand that algorithm through the lens of these new parameters. Okay.